sort of do it together so we all have similar things where we draw them. Otherwise, it makes your life a little bit confusing. So A, B, D, C are parallel chords of a circle. So the first thing we're going to do is draw our circle. A, B, and, oh, I'm sure we didn't do this one? Never mind.
No, we didn't.
Okay, now, a couple of things. When they say A, B, and D, C are parallel chords, it doesn't mean that they are exactly the same length. So we're going to draw them deliberately not the same length. So I might have a little one like here. Shall we go A, B? Yes? And then we'll do D, C a little bit bigger. Now, why do you think we're doing that? So we don't assume things that might not necessarily be true. Like if you did it here, you'd have the same and you might go, oh, it's a rectangle or whatever. So try and make them a little bit different. So we've got D and C. And what's the other thing that we should be doing? They're parallel, so we're going to pop in the fact that they are parallel so we don't have to keep rereading the question. Put all the information in as possible. Okay, AC and BD intersect at E. So what's that telling you to do? Correct. Connect the little suckers. AC and BD. Now, some of you are already talking about, oh my God, the test is going to be. I would argue that you should at least get half marks as a bare minimum for every question. Because if this, and some of you might be going, oh, I don't like a worded question. You will get marks for drawing a diagram. Now, that wasn't that bad, was it? Okay, we're going to go on. So intersects at E. Prove that triangles ABE and CDE are isosceles. So this is when we take a pause and we go, we've got two ways, I reckon, to prove that triangles are isosceles. What are the two ways? We've got two options to prove that triangles are isosceles. What's one way? Two sides are the same. So two sides the same. What's the other thing? Two angles the same. Now, which one do you think? You reckon it's going to be a little bit easier here? The angles. Most of the time when we are proving stuff, isn't it that we find, oh, this angle equals this one, da 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 da. It's to prove that lengths are the same is a little bit harder. You might have to go congruent triangles and all that sort of jazz. So I'm sort of going to try for this one, and that's what my mind is focusing on. Agreed? All right. Remember, the other tip is just do something. Now, it looks like if I was to prove that these were isosceles, this one would have to, this triangle would be isosceles with those two lengths the same. So I'm going to dive in and I'm going to let one angle be. Yep. Let it be alpha. What can I do now? Remembering you're looking, Dave, at what? Parallel lines. So, what can you see here, peeps? Look at you. Excellent, Bowen. I love it. He's picked up his sheet and he's looking at the parallel stuff. Continue, Dave.
Angle
ACD is also alpha. Why? Can't say because of parallel lines. Not corresponding. Alternate. You've got to get that correct. You're trying to prove that we've got isosceles triangles, so you're trying to prove that that one is also alpha or this one is also alpha. Why is that the case? Pardon? Think about it. Yeah, you might have said it, just not how. So look at your theorems. Get those circle theorems up. Ignore any that have center because there's no center here. Ignore any that have a tangent because there's no tangent. But there is a theorem that looks exactly like this. Yep, angles subtended by the same arc, right? So the crisscross thing. Crisscross will make you jump. That one is the same as that one. So we can now say, we could say therefore if we want, therefore angle A, B, D equals angle ACD. Why? angle, oops, angle subtended, same arc. I didn't even write subtended, but there you go. And that's alpha. Now, Mason might want to go, well, I'm going to use the same theory and say that this angle, right, this one equals this one because of angle subtended by the same arc. But Arish is going, no, I'm going to do different. What's another reason that we could say, Joe, that this would be alpha? Instead of saying it's subtended from this one, what's another reason we could say this was also alpha? Yeah?
I just have one question. For angle
One question.
ACD, is it supposed to be E instead of like D?
Hang on. Is ACD, you could say ECD, yeah?
Yeah.
But it is a straight line, so you could, yeah, I'm just going ACD. So back to, why is this also alpha? Pardon? Alternate angle. So you could, as we said, I think Mason was going with subtended by the same arc with this angle. But Joe could say that this is alternate with that one. So two different ways, both correct. Right? So what do you want to go with, subtended or alternate? Alternate, okay. So we've said, I don't know where I've left off now. So make sure once you prove something here, put it in your thingy. And then angle BDC equals angle ABD, alternate. So therefore, angle EAB or CAB equals angle DBA. Oops, I didn't call it DBA, I called it ABD. That gives triangle ABE isos, and you can do the same for that triangle at the bottom. So we're happy we've proved that they're proven. So y is AC equal to BD. Hang on, I'm coming around. And think about what you just proved in part A.
Well, if they're both isosceles triangles, then both side lengths are the same, so you just plus them together, and therefore they're both the same length.
Correct. You just proved that these were isosceles triangles, right? So what you started by saying, the sides would have to be the same. So this is the same. This is the same. Right? So we could start by saying AC equals AE plus EC. Agreed? But AE equals BE and so AE equals BE and EC would equals ED. Look, I'm just doing this. You might find a better way to write it down, by all means. I'm just, right? So, therefore, AC would also equal EC plus, oops, no, stuff that one up, would equal BE plus ED, which equals BD. Huzzah! So P is any point on a circle. So the first thing we're at least going to do is draw the circle. Now, who would like to be in charge of this? Ollie, where would you like me to put the P? Here? Here? Where my blemish was. Thank you very much. Just highlight it. That's great. Thanks. Okay, so put the point P. QR is a chord of the circle parallel to the tangent at P. Well, we don't have a tangent at P yet, do we? So let's draw one in. What is a tangent? It just glances, okay? So get a ruler. Oh. And it just glances there. I would even go so far as to write tangent here, because then when I'm looking at my circle theorems, I'm going to look at the ones that have a tangent on them, correct? All right. QR is a chord of the circle parallel to the tangent. Where would you like to draw it? I don't want to draw it as if it looks like it's the diameter. A bit further so it's pretty big. Okay, so we do that. We're going to label it QR. What else are we going to do? Put our parallel and then make the triangle. Now that's pretty good, and you've either got, well, you've probably got 2 out of 5. 2 out of 5 for drawing a decent diagram. Okay? Now we just have to prove that the triangle is isosceles. So what did we talk about before? You can either prove that 2 lengths are the same, or you can prove that 2 angles. By the way, 2 things we see here. I see the parallel lines. What else do we see? Tangent chord theorem. So if you haven't got that sheet out in front of you, get that tangent chord theorem happening. I probably do what I'm comfortable with first, like I'm looking for my parallel. So look for the Z. Would you agree? So I'm saying that angle is the same as that one. And then, if we're using our tangent chord theorem, have a look. It's saying it's not the next one. It's the next one over. So if I'm looking here, wouldn't you agree this angle here, it's not that one, but it is that one. If you wanted to, you could start with the tangent chord theorem and then use alternate angles. Right? So let's try that again. Just to make the write-up a little bit easier, we're watching. If we say let that one be alpha, so it's not the next one, it's the one after, so that's alpha. So we'll say, now, I want to refer to this angle, so we can call this T. Angle TPQ. Now I'm breaking away from what we've been doing slightly. I've labelled it alpha, but I'm a bit tired of writing alpha over here, so I'm going to say angle TPQ equals angle PRQ. If you want to put the alpha there, you certainly can, but it's more so now just so I can see my working out what I'm doing. Does that make sense? So Y, tangent chord. And now what? We're now saying that this angle is the same as this one, Y. Alternate, okay, so an angle PRQ equals, we need another letter here. What would you like to call it? Yeah, I'm not a fan of S, just because it can look like a thing. So we could go, someone said W, you could go V, whatever. Equals angle WR, no, WPR. And why was that? Alternate. Keep in mind, what are we trying to do, phrase, to make sure that it's an isosceles triangle? Another angle has to be alpha. PQR is in fact, yes, but why is that also alpha? Because no, oh, yeah, okay. Yes, it could be alternate angle. So alternate, with that, I was actually going tangent chord theorem. So again, two options. What do we want to go with? I'll write whatever you want. You prefer the alternate? Okay, so we can say angle PQR equals TPQ alternate. So when I'm reading this, peeps, I'm actually following with my fingers, you know, following the thing to say which angle are you talking about. So you've got to be specific, okay? Therefore, angle PQR equals angle, what did we call that one? PRQ. That gives triangle PQR is isos. Huzzah. Cannot emphasize this enough. And if you go back and listen to some of this, which I hope you do sometimes, what is the moral of the story here? Do something. Make sure you read the question and then do something. So two circles intersect at A and B. Yep, got that. Straight lines PQ are drawn. Now that's really important because we can now assume that is a straight line. It's not like PA and then it drifts a little bit from A to Q. Straight line. Show that XBP. So straight away we're going to go X, B, P. Ooh. Equals YBQ. Y, B, Q. Going to do something because I've got it in colour here. I'm just going to go over these lines. Oh, that's not good. Oh. What do you see? And you can't really see it on the screen, but I'm holding up my hand and I'm actually covering the right-hand side, making you just look at the left-hand side circle. And I'm straight away got kids go, oh, and then I'm covering up the left-hand side circle. Shh. So, Y is XBP. What we can do is start with our good old, let it be alpha. So X, B, P. That's alpha. Some of the people who didn't just go, oh. So we're covering up. Don't look at this. Try not to look at that circle there. What can you see in this circle? Is there a theorem that you can see? Sammy, where's your circles? Theorems. The angle's subtended by the same arc. So what else can I say as alpha? PAX? That's great, but I now want to transfer over to the other circle. Vertically opposite, right? This is a cross line here, so that is also alpha. And then, Mace, if that's alpha, angle subtended again. Yeah, that's also alpha, and therefore we've got that. I'll write it up. Again, just one version of how to write it up. Not the best, but that'll do.